Justin, I'm going to share my screen now just so I've got
Yep.
that ready.
Perfect. Yeah, morning, everybody. We're just going to give everybody a couple of minutes to jump in here, and then we'll get started right at 10 o'clock. We'll give everybody just another minute here, and then we'll get started.
Okay.
All right, we'll get going here. So yeah, good morning, everybody. Really appreciate everybody jumping into the training session this morning. We have a great topic on displacement induction ventilation with Einar here from Carson Solutions, who's going to be running the presentation this morning. Just a couple of things before we do get started. So all of the certificates of attendance will be sent out within a day or two after this session. So check out your emails for those. And then also any questions that you guys have, you just toss them into the chat, and we'll do our best to answer those as we go. So yeah, Einar, thank you very much for joining us this morning, and I'll pass it over to you.
Awesome. Thanks, Justin. Much appreciated. So as Justin stated, my name is Einar Frobaum. I'm the Director of Sales and Marketing for Carson Solutions. And Carson Solutions is a manufacturer. We'll be talking about our flagship, which is displacement induction ventilation, which might be termed displacement or floor-mounted chill beam, which has really found its home in the education market, specifically, K through 12 or predominantly K through 12, but then also higher education as well. And it does have applications elsewhere for sure, but the system discussion that we'll be stepping through today is really honed towards a classroom environment. And but know that this technology does have applications elsewhere. And so the QLC, this technology is not new. It was developed by another manufacturer about 30 plus years ago. We formed in roughly 2018 and took the technology forward. And with that, we'll get started. I give this presentation to a lot of varying groups, ranging from consulting engineers and architectural firms to superintendent conferences to ASHRAE conferences. Anyone who will talk, I will listen. I'm sorry. Anyone who will listen, I will talk. But there's 5 key points that I want to make sure that the group takes away. And that's first and foremost, understanding, the type of mechanical system that comes together. And what are the components that come together to make the system operate, understanding the differences between displacement ventilation and mixed air ventilation, and then how does the QLCI work? Seems like an appropriate item to cover. And then, what are the benefits that the students and the staff and the districts receive by applying this technology? And if you don't take anything else away, what is the home run application for this technology? What we have on the screen is a list of predominant responses from school districts of a question that I asked them, which was, when you're thinking about a mechanical upgrade, expansion, renovation, what's important to you from a deliverable standpoint? And it's, it was uncanny of how many of these responses were similar and just laid on top of each other. And it was, air quality, acoustics, thermal comfort, aging infrastructure, energy efficiency. How do we, remove the aspect of refrigeration within these occupied spaces? How do we deal with capital budgets? How do we deal with operating budgets? And so how do we use the space? So all of these things, we're very aligned with all the districts that I asked. And one of the things that I probably underestimated when I saw the responses, which was the increased demands for energy efficiency. And I don't know, and I didn't really gravitate towards it until I realized that, these energy codes are trying to squeeze the turnip, more and more. It's not like they're going back to the 1950s and 60s and saying, let's burn all the fuel that we possibly can. So how do we check these boxes that are on the screen, keep the system simple and reasonable, and check the ever popular item of the cost of the system? So keep that list in mind as we step through our discussion here today. So if we take it back to the classroom, think about, we've got 25 to 30 students in a fairly close proximity space. And if we don't bring in the right amount of outside air, we're unfortunately talking about issues like mold and allergies and virus transmission and sick buildings and sick kids. And I think, we should have been able to address that in our industry, in the 50s and 60s. But unfortunately, those things still do reside. And so one of the ways, it's not earth-shattering, but a very good and proven way to ensure that we get the right amount of outside air to these densely populated environments is to apply a DOAS, or a dedicated outside air unit, 100% outside air handler. Because in the applications where you've got partial outside air rooftop units or partial outside air handlers, do you really know that you're getting the right amount of outside air to these spaces? And I'd contend the answer is no. But I know for a fact with a DOAS unit, whatever CFM is coming in and then being pre-treated, I can quantify the amount of outside air, whatever I measure, that's all outside air, and I can subsequently quantify the amount of outside air that is going to these classrooms, right? So that's a critical item, particularly, post, COVID and pandemic times. The other item, at least as important as the amount of outside air, is the condition of outside air in these systems. So a DOAS unit is a dehumidifier, and in order to truly decouple the biggest loads, the latent loads, which are the outside air first and foremost, but the second largest component of latent contribution is the people. And so if we handle the latent load of the air and the latent load of the people, now our terminal device only has to deal with sensible heating or cooling and not have to deal with an added component of humidity in the space. So what we have on the screen, a little bit more to elaborate on that, is we have the building, we have the mechanical system, we've got the DOAS unit, and then down below, we have a corresponding graph of the representing the outside air and the supply air as it moves through the building. And on the vertical axis, we've got a general indicator of humidity. And so there's two key points on this, which are identified by, these red bullet points, which is the outside air as it goes into the DOAS unit. And the key point here that we emphasize in our system design is you need to look at the design dew point condition of your outside air. Don't just look at your design cooling day, look at your design dew point day, because that will have more moisture and more energy. And if you don't capture the design dew point day in sizing your DOAS, you will undersize it by about 10 to 15% in your market. I'm out of Minneapolis, by the way, so we're very similar markets in terms of climate. And then as this blue keel shaped represents a decrease in humidity as it goes through possibly an energy recovery device, but then a mechanical cooling. And ultimately, you've got this low point indicated here. And what's that indicating is don't just have your DOAS unit stop at 55 degrees and saturated, because that's the typical control point of most rooms. So in order to handle the occupant level of moisture, dig a little deeper, go down to about 48 to 50 degree dew point off your mechanical cooling coil, and most mechanical-based DOAS units can easily attain that level. Now you have the sponge effect to absorb the moisture contribution of the people. And now, if you start at the right peak and dig deep enough in the valley, you will take care of a lot of warts in terms of your DOAS system, in terms of your, truly decoupling the largest latent loads from the sensible loads. Two things happen. One, you make the system more efficient, and two, you make the environment more comfortable because your terminal device only has to deal with temperature and not temperature and humidity. So key point number one, this does have a DOAS unit applied, and typically a chiller, typically a boiler, and then our terminal device. And for those that are on the call that have done DOAS units, this is not a big leap of faith in terms of the technology. The only real difference is that we're ducting directly to the terminal that is in the classroom. And then the biggest difference is how that air is introduced to the space, moves through the space, and then is ultimately exhausted. So that's really the difference in other, compared to other DOAS types of systems. Here's a more elaborate schematic of that system coming together, where we have the DOAS unit that happens to be outside rooftop mounted, doesn't have to be. But in this example, rooftop mounted, outside air is coming down this central corridor. And then we have the branch takeoffs that are feeding the terminal units in the classroom, typically along the exterior wall. And then you can see these bullhorn connections. Those represent the exhaust air connection for each room that is pulling that exhaust air back to an energy recovery based DOAS unit. And then typically we do have a chiller that's producing some level of cool water for the system, possibly for dehumidification at the DOAS unit. This could be packaged DX as well, but then ultimately sensible cooling at the coil within this cabinet. And then typically a boiler that is producing some level of warm water for the system. So I say typically because in Minnesota by itself, we have 350 schools that have this technology throughout their classrooms, and about 20% don't have a chiller. And the predominant sensible cooling is addressed by the cooled and dehumidified air coming from the DOAS by itself. So it's really just a two-pipe boiler system, but then also you could tie this to a geothermal system and a heat recovery chiller or water-to-water heat pumps, and it's very well suited for that application in terms of the water temperatures delivered to the terminal devices. So key point number two, which is understanding the difference between a mixed air environment and a displacement ventilation approach. And a mixed air ventilation is doing exactly what its name implies. It's mixing the air. That could be a fan coil, a unit vent, water source heat pump, VRF, over rooftop, etc. And the point conveying is that more outside air by itself, or more filtered air, more clean equivalent air, isn't the sole point of delivering better proven indoor air quality. How air moves through a room is critically important for the purposes of better indoor air quality. And picture this. So if I'm a third grader, and the predominant way in which viruses transmit are airborne lingering particles. So it's not fomite, not surface pickup. I'm not advocating, going and licking doorknobs. I'm not. But the lingering particles that are airborne are the predominant way in which people get, infected and then become sick. So if I come to third grade and I've got a virus and I exhale, the natural tendency is that those exhaled contaminants are going to be about 95, 96 degrees. They're going to be warmer than the air in the room, more buoyant, and they're going to want to go up. And in a think about an air handler VAV arrangement or any type of in-ceiling diffuser. What is that going to do? It's going to push that air back down to the other occupants in the space. So we're not doing a good job of getting rid of contaminants in a mixed air environment. So here's a video to exemplify that. And it happens to be an overhead chill beam. And if that middle mannequin, does have, some virus, that airflow distribution is only doing a really good job of ensuring that, the mannequins on the left and the right are going to get something. Now, whether they get sick has to do with viral loading and directional impact and things like that. But you can see that just adding more of it is just going to do a better job of, a faster job of diluting those contaminants to everybody. So displacement, on the other hand, doesn't force air into the space. It slowly billows air in low near the floor, and then it effectively takes advantage of the body heat or the other heated sources in the space that increase the temperature of the air around the person and increases the buoyancy, and that air travels directly up a tight thermal plume to people's breathing environment. And there is no localized energy usage. There is no fan power connected load in the space for these diffusers. So displacement 101, the outside or the diffuser is in the classroom. And as that supply air comes out of the diffuser, it's about 63, 65 degrees. So it's slightly cooler, slightly more dense, and it drops to the floor. But it has some momentum, some velocity force until it comes in contact with the student, at which point the student's body temperature increases, the temperature around it increases the buoyancy, and you create this tight thermal plume that lifts the fresh air or reconditioned air up to the breathing zone. So the path from the diffuser to the breathing zone is much more effective in this method than delivering air where people aren't, hoping it gets distributed down, picks up contaminants, and then comes to the occupant. The other thing is that thermal plume doesn't just stop at head height. Those contaminants that want to go up, we're just going to do a better job of lifting up and away from the other students. So here's a smoke video of that same environment. Now the middle mannequin is heated, the other two are not. There you can see that low, slow velocity, quiet operation of air coming into the space, coming in contact with the heated mannequin, and then delivering that fresh conditioned air up to the breathing zone. But more importantly, those contaminants want to go up. We're just simply going to remove and take away from the other occupants in the space. So that's the general operation of displacement. So how does the QLCI work? The QLCI is a chilled beam. It is an induction unit. Use your favorite terminology. But the heart of the operation is the fresh air that's coming to the diffuser from the DOAS unit. And the typical dimensions of this diffuser is 13 inches in depth, 30 inches in height, and anywhere between 4 feet on up to 8 feet in length. And typically in a classroom, you would have 3 of these diffusers directly connected. They don't have to be directly connected, but typically they are in some fashion. But that outside air comes to this round plenum, and this round plenum runs the full length of the cabinet. And at the bottom of that round plenum is a series of nozzles. All right. So as that plenum gets pressurized up to roughly 3/10 of an inch, maybe half an inch, instead of that plenum blowing up like a balloon, it forces the air out through the series of nozzles. And as that air goes through a nozzle geometry, it creates a Venturi effect, which is an area of high velocity with a trailing edge of low pressure. And it's that low pressure creation that induces 2 parts room air for every 1 part of fresh air that I deliver. So if I, in a typical classroom, if I deliver 400 CFM of outside air to our diffusers, we will induce 800 CFM of room air that travels across the singular hydronic coil that can be either 2-pipe or 4-pipe. That room air gets heated or cooled based upon the fluid that's in that coil, mixes with the fresh air. And now in my example, those air streams mix, and now I have 1,200 CFM of supply, reconditioned supply air out to the space, moving at a very low velocity. But notice I didn't say anything about fans, motors, dampers, compressors. There's nothing to click on, disrupt the learning environment, the teaching environment. There's no constant hum of duct noise going into these classrooms. This is whisper quiet. And there's also no fans, motors, dampers, compressors, or filters to maintain in the classroom. So it's not that the maintenance goes to zero in a classroom, but it gets extracted out of the classroom and gets isolated at the mechanical room or at the rooftop unit. Do a good job of changing filters out, and you'll be 90% of the head of the curve of the maintenance of the system. So once a year, I tell the facility groups, take these 2 large front panels off each of the diffusers, expose that coil. Does it have dust bunnies or not? If it does, vacuum it off. If it doesn't, put the covers back on. And we'll touch a little bit more on this ventilation effectiveness here shortly. So typically, in a typical classroom, you're going to need to bring in 350 to 450 CFM of cool dehumidified air. Bring it into our round plenum. That will cause the induction process to occur, bringing twice the amount of room air across that coil. If we are active in cooling and we need chilled water, we are guiding design teams to use elevated chilled water so that this coil is a sensible coil only and running dry. But every coil does have a drain pan such that, if something does happen, we do have belts and suspenders to capture and what might just be a few drops of condensate should it occur. That outside, the supply air comes out of the diffuser, comes in contact with the student to create that displacement operation. So this is 2 distinct technologies in one device. So it's displacement is what's occurring out in the space, and the induction process is what's occurring at the terminal unit. So displacement, induction, ventilation. So that's cooling mode. And oftentimes this is where I get the questions from really cold places like, Buffalo, New York, and Albany, New York, and Cleveland, Ohio. And I kind of come back and say, I'm from Minneapolis. And by the way, our cold extreme is it's very similar, but we do have colder extremes here in Minnesota, and specifically northern Minnesota. And I said we had 350 schools that have this technology in our environment. If it didn't work, we would have got to school too, and they would have said, thank you, new technology, please. So heating is a very predominant and critical aspect with displacement. The key point is we don't want really warm air going out of our diffusers. And we're able to do that because even though we're going to size the equipment for January 31st and 3 a.m. and no people, that's not where we're going to operate it. You know, if I'm maintaining the room at 70 degrees, when we go into heating, we will warm up the air from the DOAS unit a little bit. We'll create that same induction process. If we are guiding the design teams and they have the flexibility to do so, you know, we're typically guiding towards low grade temperature hot water, right? So, but if we do have warmer water, that's not the end of the world. I just need to know that when we're in the design. But if I'm maintaining that stat at 70 degrees, all I really need is about 74, 75, 76 degree supply air temperature out of our diffuser that will stay low until it comes in contact with the students again, creating that displacement operation year round. And your market, just like ours, you know, that's the predominant operation, 5, 6, maybe even 7 months of the year that we're in some level of heating. So the largest school district in Minnesota, which had installed the first unit in 2004 and have now done almost all of their buildings, all of their, you know, nearly 65 buildings. The facility director stated, hey, once we installed thermal displacement into our classrooms, the number of uncomfortable complaints that they have taken simply, you know, went out the window. They just don't deal with people being uncomfortable in terms of a draft in both heating or cooling. So I think that's a pretty powerful comment from the facility director, knowing that each of those rooms has 30 different opinions of what's comfortable. Here's a smoke video of low-grade heat being supplied out of the diffuser. And pay attention to the horizontal travel of that smoke, and it's not going up until it's hitting the heat probes or the fantastic 2008 laptop and computer. So, you know, I think that's very telling. So as an alternative mechanism to heating, we can implement fin tube radiation. We deepen the coil by about 3 inches. We have 2 rows of fin tube radiation. We have inlet grills in our toe kick area, as well as multiple paths along the side of the coil for that room air to get back to the heating elements to deliver that warm, buoyant air to address, you know, the direct fenestration loss. And that's really the engineer's call. That's not our. I would say that we do maybe 1 or 2 of these designs with the fin tube integrated. And it's really an engineer's call whether they feel they need the added protection based upon envelope design or what. But it's what I would say is this example is shown as in a state university in northern Minnesota, that hopefully by the time they reach 18, 19, 20, they're not so interested in eating and chewing gum and then putting the wrappers, you know, in the grill or outlet, or, you know, same thing with crayons and pencils, even though they are pencil proof or resistant. You know, and there will be a book stop. There's like a 1/2-inch book stop. That will stop book 1 or several books if they're lined up, you know, on edge. But if they're lying flat, book 2 will probably cover the outlet. So it's just a little bit of an education piece. So I'm a visual learner. I see the smoke operation, you know, the examples that we've got, you know, like I get it. Okay, displacement, air wants to stay low, comes in contact with the heat source, and then travels upward. Okay, but does it really tell us, you know, what's happening on the molecular level? Are we truly getting, you know, cooler air, you know, down low, healthier air down low, and then warmer and dirtier air up top? And the answer is no. So we were fortunate to connect with Purdue University, which happens to be if not the leading researcher for ASHRAE 62.1 in terms of ventilation. And they lived with 3 of our units in their IAQ chamber for 2 years. Okay, so this is not an overnight or weekend study that they executed. And what they did is in this IAQ chamber, they had a number of heat sources and then a number of ladder sensors that were measuring, at 1 foot increments, floor to ceiling, the temperature and the contaminant level to prove were they getting cooler air and healthier air down low, and then warmer and dirty air up top. And so they captured that data empirically in the lab. They did so with all the units on in cooling, all the units on in heating, and then other various modes of, some units on in heating, some units just ventilating. So that the public data that Purdue captured, validated, and proved is live. It is public data. That QR code is live. If anyone's interested, they can read 30 pages of scintillating academic research. I get to about page 2 and fall asleep, so I'm going to jump to the Cliff Note version and share with you. So our industry, before I kind of get into the slide, our industry has a metric called ventilation effectiveness. And ventilation effectiveness in ASHRAE 62.1 has a chart, and it ranges from roughly 0.5 on up to 1.5. And where do these numbers come from? And I want to be clear that there's math and distinct calculations behind those. Those aren't just wet thumbs in the wind, but it's pretty basic math. And it's really to boil it down, it's a ratio of the contaminant level that's being exhausted out of the room divided by the contaminant level where the students are. And so if you look at, an overhead mixed air system, in cooling, that might be a 1, which is defined by, as in my example, 1,000 parts per million of CO2 is being exhausted, where the students are is 1,000 parts per million of CO2. So, we created unity. Conversely, in that same operation and heating, it's typically assigned a 1.0. So, I'm sorry, 0.8. And that's because as the air comes out of a ceiling diffuser, it's warm, it's buoyant, it doesn't want to drop. And the first thing it finds is a negative pressure relationship of the exhaust or return air grill. That ends up being 1,000 parts per million of CO2, and where the students are is 1150. So that system has created a better air quality that's going out than where the students are. And our industry's response is to simply increase the amount of outside air in our mixed air rooftop or air handler. That in no way, shape, or form guarantees, just because you add more air at the air handler doesn't mean that you're going to get that fresh air is going to get to the students, particularly in heating. So conversely, if you have a ventilation effectiveness that's defined greater than 1, that means the air quality that's being exhausted is 1,000 parts per million in my example. And where the students are in cooling, the default value is 900, resulting in a ventilation effectiveness of 1.2. We got a better air quality where the students are than what's being exhausted. That seems to make some pretty good sense to me. So what they proved is that the QLCI, we actually outperformed traditional displacement ventilation, 1.3 to 1.2, but more importantly, in heating, Purdue validated that our system, the ventilation effectiveness was never ever below a 1, and it went up as high as 1.2. So we're always in displacement, whether we're in heating or cooling. So that is a critical component to better indoor air quality, but also energy efficiency. So in terms of energy efficiency, and here's that chart that I was referencing for those that aren't familiar. In ASHRAE 62.1, up here is the mixed air system component, and down here is the displacement or stratified air. But the key point is that's a finite list to possible ventilation designs that is limitless. Close. ASHRAE recognized that this chart has limits. And so they said you can either use the default values in the chart on the page before this in version 2019, they stated you can either use the default values in the chart or you can go measure it and test it. And if you test your ventilation system, you have to do it empirically, you have to CFD model it, and you have to do it in heating and cooling. Purdue knew what they were doing ahead of the game. So the benefit of that is because we've tested it, we don't have to use any of these prescribed, quote unquote, default values. And here's the aha. The biggest energy hog in this system is the DOAS unit. Even though it's 1/3 the size of most rooftops and air handlers, it's still, moving an inefficient medium, which is air. So if we can downsize the air moving device, we can create a huge energy impact to this system. So for comparison's sake, let's say you're evaluating, I really like DOAS and fan coil, or I want to investigate this DOAS and displacement induction thing. So I've got a 10 classroom wing expansion that's going on, and I need to determine how much outside air I need to bring into each of those 10 classrooms. With a DOAS and a fan coil, I do the math on the students and the square footage, and then I apply this denominator, ventilation effectiveness. Cooling, it's a 1, heating, it's a 0.8, and net result is in heating, by code, I have to bring in 510 CFM of outside air to each classroom, times 10 classrooms in my example. That DOAS is 5,100 CFM. Conversely, if I look at doing this design with our displacement induction ventilation, do the same math on the students and the staff, or the square footage, divide by a bigger denominator, which results in a smaller answer. Now I do need to double check with the reduction of outside air. Do I meet my latent load? Sometimes I don't. So let's say I have to add 20 CFM. So let's say now I've got 360 CFM up by code to each classroom times 10 classrooms. That DOAS is 3,600. 3,600 versus 5,100. The DOAS unit for this displacement induction ventilation is smaller, lighter, more efficient, smaller FLA, MCA, MOP, smaller ductwork. That system benefits the mechanical system with about 6 efficiencies that the mixed air ventilation approach did not. So that's a huge benefit. I'm going to jump to this. Energy efficiency. This is one of the best, what I'll call controlled experiments that I can share because it's public data. 2 identical schools. So the first school, Oxbow Creek Elementary School, was built in 2010. And it was based upon an air handler, VAV, air-cooled condensing unit, condensing boiler. But the state of Minnesota, all the public buildings, public schools included, have to report their energy utility usage, I think quarterly, to this entity, and it's available on a website. It's called B3 benchmarking. And to heat and cool that one building, and that snapshot was $123,000. And I think that was in 23 that I captured that. I think it's $160,000 now. That same architect and engineering firm designed and built 2 brand new buildings, Brookside and Sunrise elementary schools, identical to Brookside, or identical to Oxbow Creek, sorry. When I say identical to the brick, like they did not change anything. but they changed the mechanical system away from an all-air system to a decoupled DOAS-based chill beam in the non-classroom spaces and displacement chill beam in the classroom, air-cooled condensing boilers. The cost to heat and cool that same building, identical building, 15 minutes away is $50,000 less, 40% energy savings. Why wouldn't we do this? I mean, this is like, this makes no sense. That the why do we see the savings? And it's not just one big cut. The biggest cut is over here. This is moving a whole lot of air that's wasted. Air is not an effective heat transfer medium. Water is much more effective in terms of addressing BTUs in a system. The smaller DOAS unit, the smaller air-cooled condensing unit, the application of displacement induction, all of these layers add up to this savings. That's $50,000 times 25 to 30 years for two comparable buildings. So I asked the question, why wouldn't we do this? So I apologize for the font and the array of information on the slide, but that question was put to one of my favorite repeat offender engineers, and the GC said, you're going to blow the budget by $800 to $1 million with this DOAS and displacement induction ventilation thing. And that engineer, took it upon himself to prove him otherwise, which is he looked at a school that he designed with air handler VAV, captured all the live bid data, all the labor rates, all the piping costs, ducting cost, controls cost, and he boiled it down, inflation, labor rates, and he boiled it down to about $52 a square foot. He did that same analysis on the more efficient building that I showed on the slide before. Live bid data for equipment, material, labor, ducting, piping, blah, 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 fill in the blank, $52.90. So essentially, he proved to the GC and his owner client that why would you do something that costs you the same that is going to cost you for 40% more for the next 30 years. That next school went with DOAS and displacement induction ventilation. So if the cost is the same and you're going to recognize all this energy savings, why wouldn't you do it? And this, even though this is new construction that I'm talking about, this is perfect for renovation as well as new construction. And I would say a high majority, about 75-80% of the projects that we do are renovation work, not new construction, just because most school districts are doing renovation of existing units or aging units. Thermal comfort. A lot of times we get pushback from architects, like, oh, you're going to put something on the floor, you're going to take up floor space. I said, architect, we're actually going to give you more floor space because you can actually sit directly next to us, next to the unit if you need to. I don't promote that, but invariably it happens. And for every square foot or every foot off the wall that I take up, I give back as usable bookshelves. You can put plants, books. I don't have air coming out the top unless I apply the rear fin tube mechanism. So Jenny sitting here with her exposed Birkenstocks, if she felt a draft, you can put your hand right up our diffuser, right on the diffuser outlet, and you will not feel a draft. That velocity is so slow that Jenny can sit here. If she felt a draft, she'd complain. They wouldn't leave these rooms in this arrangement. Same thing with Billy and Bobby sitting here. If they felt cooler or warmer than Becky or Sue on the other side of the room, someone would complain. They wouldn't leave these rooms like this. Acoustics, thermal comfort, acoustics, because we don't have any constant, duct velocity drone hum, and we don't have any compressors or fans or dampers actuating, we can create better learning environments, better teaching environments. So these things are whisper quiet. Maintenance, this is air, it's water, it's not complex. We're not dealing with, chasing refrigerant BTUs here and there. We don't have the concerns about A2L aspects that we need to deal with in our design in an occupied space. We're not changing out motors or fans. We're not changing out filters in the classroom. Again, that's the maintenance doesn't go to zero in the system, but it gets isolated or removed from the classroom. Kids are hard on equipment. These kids, I have 4 of them. They're all ding dongs. They just happen to be in their 20s now, but they're still ding dongs. And they will try to, wreck things. And so this cabinet, each and every one of our cabinets is constructed with 16 gauge, heavy gauge steel, multiple 90-degree bends around the perimeter, multiple 90-degree bends around the panels, center mullions. I can stand on this thing, jump up and down. I won't deflect it. I can't deflect it. High grade powder coat, textured finish, doesn't pick up fingerprints. I've been to the first one that was installed 22 years ago. It's still in good looking condition. All the water piping, it runs behind the unit. You can get louvered fronts, perforated fronts. Every coil's got a drain pan. The architects can, build up whatever countertop. Our standard is, sheet metal, but I've seen, laminate and solid surface countertops applied very often. Like I said, a majority of our work is renovation of unit vents and unit vents that might have had associated casework. And so one of the things that I often hear is like, please don't lose our bookshelves. I'm like, we're going to destroy your bookshelves because we might take up 18 feet of a 30-foot wall with our diffusers that we need. But what do we do with the remaining 10 or 12 feet? That's where we can start complementing our array to give them a wall-to-wall finish of bookshelves, utility cabinets, ducted bookshelves, blank fill sections, vertical duct covers, whatever the school district wants or what you want to deliver for your client, we can deliver. We can do recessed units, custom cabinets, custom colors, custom, countertops can be applied. Here's a example of sort of concept to design. The engineer first pass at an elevation view, showing, windows and directly beneath the windows, the displacement induction diffusers, integrated shelving units, custom bookshelves between the windows, and then the outside air duct covers in each of the corners. And what the architect positioned with the school district said, school district, you have a whole bunch of cinder block wall and not a lot of natural lighting. And what we're going to give you is a whole lot of natural lighting and a single piece of HVAC equipment that ventilates, heats, and cools all as a piece of usable furniture by your students and staff. School district said, Yahtzee, that's exactly what we're looking for. And this is what we designed. And so in these renovations, the biggest hurdle is how do you get the outside air to these spaces? But it's worth fighting for. But go back to the system. This is a DOAS-based system that's bringing in code minimum OA only, 350 to 400 CFM. So in a lot of these classrooms, we've got 14 inches between the drop ceiling and the roof line. That doesn't lend itself well to rooftop VAV or air handler VAV, where you got to bring in 18-inch duct or 20-inch duct. 10 or 12-inch duct coming into the room. In this example, then we teed off to the left and to the right with 8-inch duct. And then we dropped the outside air in the left corner into QLCI1. As it left QLCI1, that outside air traveled through a ducted bookshelf into QLCI2, and over on the right, that outside air, half the outside air then also came in on the right-hand side into QLCI3, left QLCI3, passed through a ducted bookshelf, and the air from the left and right drop then simply balance out. There's not a physical divider in the middle of QLCI2, but that air plant, once you balance at this air balancing device, that outside air has nowhere else to go but to our diffusers to create that constant. It doesn't have to be this layout. You know, what if you had a 1940s, 1950s building that had a lot of columns? That wouldn't lend itself to this nice, you know, continuous outside air duct. If you had a column, a lot of times in that example, we'll straddle that column with an, you know, an outside air drop on the left and an outside air drop on the right, and then feed the outside air to your left and to your right. So it doesn't, it's first science. We've got to meet the heating load, the cooling load, latent load, ventilation load, and then art. And how do you put the Lego pieces together? So here's a couple examples of different arrangements. The top two are new construction, outside air in many of those cases where they're sheetrocked in. This happens to be that same Northern Minnesota State College where they're applying the technology at the back of the learning classroom. And then a brand new 500,000 square foot high school in Massachusetts, where outside air was dropped in the left corner and fed one unit towards the center up until the bookshelf in the middle. And then over on the right, the outside air was dropped down to sheetrock chase and fed the unit on the right up until that bookshelf. And then on the lower portion, this is Salmon River or Fort Covington, New York, just south of the Canadian border. Outside air is dropped in on either side of a column and feeding the diffusers to the left and to the right. Same thing in Beloit, Wisconsin. Similarly, center drops feeding left and right QLCI units. So notice that people, I get the question, well, what if they have operable windows? Like, tell me, maybe these guys do, maybe they don't, I don't know. But this is a 1950s, 60s building. It's got operable windows. I don't care, particularly with our QLCI units. Now, people always say, well, what if it's 85 and humid? And they open the window. Like, well, why are you opening the window on an 85 and humid day? But I understand people do some weird things. So, what do you do in the non-classroom spaces? Oftentimes I'm seeing overhead chill beams applied. We do manufacture those as well. It's a nice complement because it uses the same outside air, the same chill water, the same hot water. You keep the mechanical system congruent throughout the building, same no moving pieces and parts. Different, you know, technology. It is a mixed air system, but they're in less occupied spaces, so less densely occupied spaces. So the aspect of, it's not that IAQ isn't important, but it's important to a lesser degree than I'd say a densely populated classroom. They don't have to be chill beams. They could be water source heat pumps. They could be fan coils. They could be VRF in those spaces. It plays nicely with other system types if you need to. So it's not, the displacement induction ventilation device is the dumbest piece of equipment in this system. Same thing with the chill beam. Okay. These devices don't know anything better than to work. Feed it the right amount of outside air, feed it the chill water, the hot water. It's just going to do its job. Okay. But applying the DOAS unit, that device helps ensure that we get the right amount of outside air, proven outside air to these spaces. That's so important. Doing a better job of dehumidification makes the system more efficient, and it helps create a better thermal comfort environment. Excuse me. Applying displacement gives you the better indoor air quality because we're purging contaminants, gives you quieter operation because we don't have any moving pieces and parts, gives you better thermal comfort because of the slow moving, much more moderate temperature air. It's easy to work on. It's air, it's water. It's less maintenance because we don't have any moving pieces and parts. We don't have any refrigerant in the occupied spaces. We don't have to deal with that in the design, or worse, if something bad happens in operation. And 20 to 35% more is so conservative. I wrote it. I mean, I showed you the two identical buildings. That's a 40% savings. So, and for system costs that are very comparable to other well-designed systems. Now, the discussion point is, what's a well-designed system? I'm happy to have that discussion, because there are definitely not well-designed systems that I get compared to. So, and the home run application is for sure aging unit vents that need to be replaced. Maybe we can take advantage of the hot water and chill water that's already there. We can give them that same look and functionality. We can give them the shelving. We're going to eliminate the noise and the draft concerns. You know, Jimmy can actually sit here without, getting disturbed by a draft or a noise concern. You can actually put plants, books, whatever, on top of all of our cabinet. Unfortunately, I've been in a number of classrooms that had unit vents that those outlet grills get covered, or worse yet, I've seen a deflector shield put over this outlet diffuser to ensure that they blow the air out. Okay, I mean, it looks horrible, and it's a band-aid approach for a bad system design. We're going to save on energy utility, and we're going to deliver the known amount of outside air that's so critical. How many times do these unit vent systems get their outside air damper shut off for, they don't want to freeze the coil, they don't want diesel fumes coming in, they don't want insects, dust, grass clippings, etc. And that's what happens, because it's an easier fix than having to deal with that damper being open. I said geothermal, you can tie these to geothermal. It's a nice fit. It just only adds to the energy efficiency story if you're going down that path. I won't hit you with that. But these are just some things of reinforcement. The heart of the system is the DOAS unit. We've got to apply the DOAS unit. The 5 key benefits: better indoor air quality, better thermal comfort, quieter operation, less maintenance, and more efficient. Ventilation effectiveness that we can apply is at least a 1, sometimes it's 1.2. It adds to the energy efficiency story of being able to downsize your DOAS unit. And then, one time a year, change out, that one time a year, vacuum the coils off if it needs to be. And, the home run for sure is your aging unit vent that needs to be replaced. So I just want to say, thank you, Justin and Odell HVAC Group, for allowing me to have a conversation and introduce I think a differentiating technology that checks so many boxes for an environment that needs these boxes checked routinely. So thank you very much. And I don't know if there was any questions that came in, Justin.
Nothing yet, but if anybody has any questions, feel free to put them in the chat. We can take a couple minutes here to answer any questions. But yeah, thank you very much, Shiner, for the great presentation there.
All good.
Yeah, once again, certificates of attendance will get sent out within a day or two of this presentation. We also keep all the recordings of our webinars on our website, so if you want to go back and take a listen, and we can also share the presentation with everyone on this call. And if you do have any questions that come up after the fact, feel free to reach out to your local Odell rep, we're more than happy to answer any questions or work on any applications with you guys.
Justin, was there a Q&A that came up, or was that just a comment? I just saw
No,
red.
just some comments saying, yeah, thank you for the presentation.
Okay, you're welcome. You're welcome. No, thanks everyone, and I hope I get 2 thumbs up for actually being under the time slot. So
yeah. All right, yeah, it doesn't look like any questions are coming through, so we can leave it at that. But yeah, thank you everybody for your time today, coming in and listening to the presentation. And thank you very much for giving the presentation today. And like we said, if you have any follow-up questions, feel free to reach out to your local Odell office, and we're more than happy to help out.
thanks, Justin. Appreciate it.
Have a good day, everyone.
Yep. Bye.